Hi, in this video, we're going to, so recall that we just learned how to construct measures by using outer measures. Now we're going to be more specific by study Boreal measures, and then we will introduce Lebesgue measures. Okay, so let's get started. I am going to state a very important theorem. This concerns about the construction of a Boreal measures on the sigma algebra generated by the algebra, which is generated by the elementary family, consists of H intervals. Okay, so this is a proposition 1.15 in Poland, and the statement here is equivalent to the statement in the textbook. I will use a slightly different statement just because my way to state the claim also includes the possibilities that the intervals could be any form. For example, it could be in open interval A, closed interval B, or it could be negative infinity, comma B, closed interval, or open interval A, comma infinity, closed interval. So it uses all form, and then it's kind of convenience to, without concerning any other cases during the proof. Okay, so here the proof. I'll try to write well. So let f be a continuous function from R to R. So it is increasing and continuous. And we're going to define a function mu naught. Okay, so this is the elementary family set, consists of H intervals. Okay. And you need to recall that collection of finite disjoint elements form an algebra. And then this proposition is about the premeasure, is about the construction of the premeasure on this specific algebra generated by this elementary family of H intervals. Okay, so define mu naught to be, its domain is E to R, and domains from E to R by mu naught of I is equal to sup H interval AB that is subset of I of FB minus FA. And mu naught of empty set is equal to 0. So that is the definition for our mu naught. And this extends and then claim. So this is given, and we will use this definition in our proof. So claim is mu naught extends to premeasure on A, where A, the premeasure generated elementary family of H intervals. Okay, so I'm going to draw like, so here we have E, and then here we have A. So right now our function defined only, mu naught only defined on E, but our claim is that you can use the exactly same definition, but the domain, you just simply change the domain from E to A, and that is called extension of mu naught on A. and then we're saying that extension is a Premeasure on the algebra A. Okay, I hope this is clear. So now let's prove. How do we prove this? Let's make, so the whole structure, so the proof is kind of long and it is a little bit technical. And then the outline, so the outline for this proof is so outline. So A is show for all I in this E, mu naught of I is equal to, so for all I in E, I is equal to union of In, mu naught of the union of In is equal to countable union is equal to infinite series of mu naught of In. So that is our first claim. Let's check. Right. Okay, and then what about the second one? So let's once we show this, we're actually done because recall that finite, so ions are disjoint, right? Ions are disjoint sequence, and In is in E as well. Okay, so recall finite disjoint of elements in E elementary family is an algebra. So in order to extend those, right? So mu naught now is from A to I. So for every set in A, it could be written as finite disjoint intervals. Okay. I will so mu naught A is equal to mu naught of the union from ik is equal to 1 to n. Notice it is finite union of ik, right? And then we have 1 to n of mu naught of ik. And then that is how we define, how we extend the function mu naught to the domain A rather than just the elementary family sets. Okay. So you need to show this definition of mu naught from A to 0 positive infinity is well defined. And then when you show it is a Premeasure, right? So show it is a Premeasure on A. So there are two sets. One is mu naught of empty set is equal to 0. And then the other side, as long as there is infinite series, an infinite union of these joint sets contained in the algebra A, then the Premeasure should have countable additivity. And that is true naturally because of the claim 1. Mm-hmm. So that is the structure of this proof. It is like you first introduce a function and that function only defined on E, and you want to extend that function. And how to extend by simply change the domain to A rather than E and nothing else. So the definition of the function does not change at all. And you just extend its domain. And then we need to make sure, first of all, the function mu naught has countable additivity is this, or you can call sigma finite additivity. And then the second one, you need to make sure that after we extend this function on A, is this well defined? Because express the input of this function mu naught in different ways because of the nature of the union, right? If you look at one side, and it could be expressed in infinitely many ways, because there are infinitely many ways of combinations to write down equal to some unions of some different collection of sets. So show it is well defined, and then right after we show well defined, we're almost done because we just need to show it as a premeasure, and that's pretty simple because the work we have done before. This is comes natural by the definition of mu naught, and for this is just it is just by one, right? As exist in for the union algebra, then the countable additivity holds, and that is by one. Okay. So what I'm going to do is I am going to only show you how to do the claim one, because that's the majority of the proof. Okay, let's get started. Okay, so proof of one. So again, it is hard to prove the equality directly. So we're going to prove one-sided equality first and then the other later. So let's prove this first. Okay. So so the idea of this is you don't want to deal with infinity. So because it's always give you some trouble. So what we're gonna do is we're gonna set our in the context of finiteness, and then we can order things however we like, and then we just take the supremum. So that is that's very standard technique in measure theory. And as I practice these days, I feel like it's very common to use this trick. And that's why I also want to make a video of this proof. Okay, so let J be a finite subset of the natural numbers. So this is just our index set, okay? And then we enumerate this, it be J1, J2, Jn. Okay, so I have this. So why do we want to do this? Well, for so let I so we're going to do this. We're going to do the big interval I, and I'm going to do small intervals. Okay, and this is a finite many small intervals, and the union, and they're disjoint, and the union of them is equal to the big. Okay, so let's look at the formula. Mu naught is equal to, so recall definition for mu naught, right? Mu naught is equal to supremum of FB minus FA, where AB over the interval AB subset of I. Okay, so peak, let's see. So let's name them first. So this is equal to AJ1, this is AJ2, this is AJ3, AJ4, and this BJ4. Okay, so we pick A JK, B JK, each interval inside of I JK. For example, I'm going to pick this. Okay, and we observe that mu0 I, okay, is larger or equal than FB minus FA. Why? Because mu0 I is equal to supremum of FB minus FA, where AB is subset of I. So what we are doing right now is we have interval I and we have AB where we set this equals to B rather than, so this is I, right? So the whole interval is I. Let me change a different color. So this is A, and let's see, B is equal to BJN. Okay, I'm sorry, this is not BJK. This is BJ4. Okay, so we're doing this. This is B. And then as you can see, right, this holds, this inequality holds. And then, so that is the first observation. It's like you have your interval I, and you split your interval into small intervals. And then what you do is you look at those connections, right? And you name them AJ1, AJ2, AJ3, AJ4. And for, and then you also name, so BJK, B, B here. Right, that's how I wrote here. That's how I wrote here. And then for the last one, you just name it B, and that is your A and B. And then because this length is less than this, the set, right? This set is bigger, and by monotosity, let's see, right. Oh no, by the definition of this, because it is a supremum, and of course that this AB just one possible element in the when you consider it. So this is supremum. So therefore, it's definitely larger than FB minus FA for this specific choice of A. And then what do I do is equal to FBJN minus FAJ1, right? And then we are going to do telescoping sum. So this is equal to FBJN minus FAJN plus FAJN minus FAJN minus 1 plus dot 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 plus FAJ2 minus FAJ1. Okay, and then this canceled out, this canceled out, this canceled out. Therefore, the equality remains. Okay, and why do we want this? Well, this is equal to summation. I is equal to 1 to NFBJI minus FAJI, I guess. Right. Okay. Except there is a different detail that we need to be careful. So here I'm going to write them separately, and you will see why. So this is equal to this plus summation k is equal to 1. I guess I was using k here. sorry. So this is equal to, sorry, I guess this should be n. I don't want to confuse you just by the notations. So k is equal to 1 to n minus 1 and fj aj k minus, sorry, right, fajk minus fajk minus 1, right? Okay, so if k is equal to 1, okay. Oh, actually it should, I should write this. So I should write this because I have, when k is 1, so I have minus fajk, and when k is equal to n minus 1, so I have minus ak minus 1. Yes, so this is going to be fj, faj, k. Okay, so I have this. And this is going to be large or equal than fbjn minus fajn plus, we're going to use the monotonicity of f here. So this is smaller or equal than this. Because ajk's are those points. So this point is definitely larger or equal than any point over here. And then by the monotonicity of function f, the value evaluated here is definitely lower than the value evaluated over here. Okay. And then what do we do? And then we can combine everything together, right? So this is equal to summation. K is equal to 1 to n, and we have to. And notice that here it is finite, so we always, but actually we don't need to order in this way. Okay. So I'm gonna just write so the index over here, they help us to order things. So I know there's interval I1 is in front of I2, in front of I3. And the reason that we want that nice order is like when we're doing this, right? We're doing this. But now we actually don't need them anymore. So I'm just gonna say J is in J of FBJ minus FAJ. And notice that this is going to be, so because since mu naught I is larger or equal than J is equal to J, FBJ minus FAJ for every possible ways of splitting. So every possible ways of picking AJ, BJ in IJ. Okay, so we're going to take the supreme. So so that implies mu naught of I is still larger or equal than J supremum of A, BJ, subset of IJ of FBJ minus FAJ. Okay, and what is that? That is equal to J is in J and mu naught of IJ, right? Okay, and then notice that this is a finite sum, right? Since mu naught of I is larger or equal than finite sum j is in j mu naught of ij for every j, that is the subset of n. So take the supremum, right? So mu naught of I is larger or equal than any supremum, right? So basically any j. So I can say j is equal to 1 to infinity mu naught of ij. Or we can actually change this to n of in. Okay, and then we're done with this inequality. So let's just go over again, what are we doing here? We want to show the equality, so it's better to start with one side inequality here, right? And because when you look at the infinity, it is really hard to deal with the infinity. So what we're gonna do is we're gonna make our problem simpler using two steps. The first step is we pick a j, which is a finite subset of natural numbers, and this tells us how many numbers of the interval we have. Okay. J N. Okay. So you have a big interval I. You have a big interval I, for example, right, from E, and you can only look at, you decide to only look at this specific interval. And you can write that specific, so you have a long line and you only focus on J, which is finite number of this. So maybe this, you only look at this part. So that is J, and it tells you how many intervals you are looking at. So that is a finite number. And once we have that, we actually pick AJK and BJK from each IJ. Okay. And then the reason that we have the index, sub-index K, is we want those small intervals to be in certain order. So we pick AJK and BJK from each IJK, and because and as I illustrate here, and we let A1 to be equal to A, and we let BJN, which is we call that AJN and BJN, they are selected from the interval IJN, right? So the last interval that we're considering using the finite subset J of natural numbers. So we have A and B, and then by monotonicity of, and by definition of mu naught. So AB is just the one possible interval inside of as a subset of I, right? And mu naught I is equal to the supremum of FB minus FA, where AB is all over, we're comparing the H interval AB over all possible H interval AB in the interval I. And here, if we set in this way, we have one choice of A and one choice B, and this is definitely going to be smaller or equal than the supremum, right? And therefore, what do we have? We have this inequality. And once we have that inequality, we just rewrite it, because we name B as we name BJN as B and AJ1 as A. And then we keep continuing a tidy scoping sum. And we forgot about the last term, we only focus on this terms. And we use the monotonicity of F to get an inequality of this. And therefore, this is started with B, and this is also started with B. And then we're actually in good shape, so we can rewrite them in this way. And then now we don't need the order anymore. So we're just gonna write a finite summation where lowercase j belongs to the capitalized J of fbj minus faj. Okay, and then we need to continue, right? So we know that f naught I is larger or equal than um, um, larger or equal than this, where aj and bj, they are really arbitrary subset of ij. And we can actually do over that. So notice that when I said I give 2 steps to make this problem simpler. The first step is choosing finite subset j of n and only look at finitely many interval in I. And then the second step is actually to choose a, j, k, b, j, k, and only focus on the fixed one. And because it is arbitrary, so the final inequality we get over here works for every possible ajk, comma bjk. And therefore, it is smaller or equal than the supremum of that. And what is the supremum of that is mu naught ij. And therefore we have this. And since we only consider finite, we need to take supremum somewhere else, right? So once we have this inequality, and we know that this j is actually arbitrary. So we take the supremum j over j in n. So therefore we have this inequality. Okay, and then let's do the other direction. So show that this is smaller equivalences. Well, you might first think, well, using sub-additivity, but that's not true because we haven't defined, and actually that is our goal, that this is a premeasure, okay? So we cannot do that, and we have to use some inequalities and working with H intervals. Okay, let's keep doing. So what do? Is we let, and I named this I, okay. So let AB in I, and let IN intersect AB, and this is equal to AN, BN, just we call it, where N is in N. Okay. And then notice that because I is in E and this is in E, so this is in E. Okay. And then we need to use the right continuity of F. So by the right, so what we're gonna do is we're going to use compactness, but compactness only work for closed interval, and we have like H interval, which is not technically compact. Therefore, we need to work with compactness, right? So we can extend our interval a little bit, and that's why we need right, but not too much. And how to control that is to use the right continuity of the function f. So by right continuity of f, okay. So therefore, all epsilon larger than 0, there exists a delta such that f a plus delta minus f a. We don't need an absolute sign because the monotony of f smaller than epsilon. And we also have for b. So there exists epsilon for each bn. So b epsilon n such that f b n plus delta minus f p is smaller than epsilon over n. And you might wonder why. I feel like there's a there's a general pattern, like whenever we're dealing with something in small pieces, and then later we're going to glue them together, we kind of use this type of epsilon rather than just epsilon. Okay, and then we'll see how we glue them together later. So so what I'm thinking is so this is A. So this A plus delta, and this is B, and this is B plus delta, and this is the interval AB. Okay. For example, EN. Okay. And then what is a compact interval? Well, this is a compact interval, right? So A plus delta, comma B is compact. And actually, what we need to do is because this is a compact interval, and there is open cover, which is an bn plus delta n, okay, is an open cover of a plus delta b, right? And because it is compact, there is finite. So, and we know a plus delta b is inside of union n with a and b plus delta n. And then there exists, let's call it n, such that the compact interval a plus delta comma b is a subset of I k is equal to 1 to n of a k comma b k plus sorry, jk plus delta jk. Okay, so what are we doing, right? So once we have this, what is the next step? Eventually, we want to prove this inequality. And notice that jk. Notice that we have ajk plus 1, for example, and this is ajk. And so this is bjk, right? But it is possible that we add the epsilon, so bjk plus delta jk. So this is larger or equal than ajk plus, strictly larger than ajk plus 1. Okay. And because we're dealing with finite lists, so we can order them in the way that about this collection. So notice that it has to be this. If it's not, if ejk plus delta jk is smaller than ajk plus 1, then it's find. So it is not going to be totally cover the interval a plus delta comma b. So we're looking at the collection of a jk comma b jk plus delta jk. Okay, and then now we call our goal, right? So we have FB minus FA, okay, and then that is equal to, since FB is, I need the right continuity, yeah. I need FB is, so FA, we're going to replace FA. So it's equal to FB minus, and then you look at this. So minus FA plus delta minus epsilon or plus epsilon. FA. Yes, right. That is by, let me label it. Okay, so, and then what do is we're going to replace something. Why true? Because B is large or equal than, no, because B is smaller or equal than BJ n plus delta J, and notice that B is equal to BJ n. So quality holds, and A is equal to AJ1. And then again, once we use this, we can start with telescope. So this is equal to FBJN plus delta JN is going to be smaller than this plus this minus FAJN, okay, plus FAJN minus 1 minus FAJN minus 1 plus FAJN minus 2, and then plus dot 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 plus F, I want it to be minus AJ1. Right. It should be minus F AJ1 and then plus epsilon, and that's it. Okay, so here I see I made a mistake. What I'm gonna do is so this is actually plus AJN, and then we have minus AJN minus 1, and then plus AJN minus 1, and then till we have minus AJ1. Okay, so those are all canceled out, and the only thing left is this and this, which is exactly this. That's why we have the equal sign. And then we can write this as BJN plus delta JN. And then we have negative FAJN plus the k is equal to 1 to n minus 1 of fajk plus 1 minus fajk. Okay, so we have this plus epsilon. Plus epsilon. Okay, and then now what can we do is, since we have these terms, right? I think we're gonna use again the monotonicity, right? Otherwise, what's the point? Okay, so smaller or equal than f ejn plus delta jn minus fajn plus summation k is equal to 1 to n minus 1 of fbjk plus 1 minus fajk. Okay, plus epsilon. Okay, and then look at this. J. Right. Sorry, I mean to write this plus delta jk plus 1. Oh. Oh, actually, no, because it's not going to be plus anymore. Why? It's just going to be k, because this is your ajk and this is ajk plus 1, but this is bjk plus delta jk. So this into, okay, so we have this, and look at this, right? We do have some approximations on this. So it is going to be smaller or equal than bn is smaller or equal than fbjn plus epsilon over 2n minus fajn plus summation k is equal to 1 of fbjk plus epsilon over 2n to k minus fajk, okay, plus epsilon. Then what we have is we have summation k is equal to 1 to n fbjk plus epsilon to the power 2k minus fajk plus epsilon. Okay. And then what do we have? Because the all matter anymore, right? We can get rid of k, and then we can just say summation n in n. So, well, let's see. This is smaller or equal than n in n of everything, because the sum is a larger set, right? Change the index to n. Okay. And then what do we have? Well, I think that is smaller or equal than epsilon times epsilon, right? Yes, epsilon. So this is equal to summation n in n of fbj n minus fajn. Okay, and then plus 2 epsilon. Okay, so what remind the goal is this. You can see here is mu naught of an. So this is going to be smaller equal than summation n is in n supremum of f of bjn minus f of ajn. Okay, so ajn comma bjn is a subset of in plus 2 epsilon. So this is equal to summation n mu naught of in plus 2 epsilon. And then if you look at this, this is going to be So A, B are totally arbitrary. It takes supremum on the left-hand side, right? Right. So since FB minus FA is smaller or equal than this, for arbitrary selected AB. So let's take the supremum. We have so supremum of AB over interval I of FB minus FA is smaller or equal than summation n of mu naught of IN plus 2 epsilon. And this supremum is just equal to mu naught of I smaller or equal to, therefore smaller or equal than this, right? And then we're gonna take epsilon goes to 0, therefore we obtain this, okay? And together, so together, we have the equality, and then we're done with proving this, okay? And then what do we need to do? So define mu naught from A to 0, positive infinity, okay? By mu naught of mu naught of I is equal to supremum of AB of mu naught of FB minus FA, and mu naught of empty set is equal to 0. So that is our new function. So we still need to first show that mu naught is well defined, right? How do we show it's well defined? Consider I is equal to union of AJ the union of K K I, okay? So mu naught of I is equal to, so I want to show different representation give me the same answer. So the mu naught of AJ is equal to supremum. Let me think about this. Let's do disjoint, where AJ, KI are disjoint sequence of sets. You can do any, but and then once you have a union, you can disjointify it. So that's why we just show with disjointified union. Okay. Sequence of union in E. Okay. So we have mu naught of union of A is equal to summation mu naught summation mu naught of union of AJ intersect union of KI, right? Is the mu naught intersection, or let me think. Union of AJ intersect mu naught of union of AJ intersect KI is equal to mu naught union of AJ intersect KI. Okay, so here is about I, this is about I, this is about J, and this is equal mu naught J. Oh, sorry. This is equal to summation, right? I J mu naught A J intersect KI, and we can now switch. Let's see. We can switch. So this is J. This is I mu naught A J intersect KI. which is equal to I should add that this is equal to summation j. Let's see. Or maybe not. So we have this, right? And once we have this, we can switch the summation. And once I switch the summations, I can again using backwards. So it's going to be mu naught of union of ki. Oh, actually, I think I did this wrong because what we try to show is we try to show, of course, that if union of aj is equal to union of ki, then mu naught union of aj is equal to mu naught union of ki. But what I really need to show is that because we claim this is equal to j mu naught of aj, right? And we claim this is equal to I mu naught of ki. So whether or not those two are the same is a key question. So there to convince the audience those two are the same. Okay, and this is equal to right. So this is equal to j mu naught aj intersect x, right? So this is j mu naught aj intersect what is x? X will be union of I of ki, and this is equal to j of mu naught union aj intersect ki. This is I. Therefore, we have j, we have I, we have mu naught aj intersect ki, and because the summation we can exchange, so this is I, this is j. And because each term are negative, and therefore I can interchanging them. And therefore we have mu naught of aj intersect ki, and then going backwards, we obtain I mu naught of a of ki, right? And then therefore they are indeed the same. So mu naught on A is well defined. Okay, so lastly, show that mu naught is a pre-measure on A, right? So the first thing is mu naught of empty set. By definition, is just equal to 0, so we're done. And the second thing is let E1, E2, the disjoint of joint sets, okay, in and the infinite countable union of I is also in A, and we have EI also in A. Right, so since we have this, right? So what is E1, E2? They are finite union, they are finite disjoint unions, right? So eventually I want to show that mu naught union 1 to infinity of EI is smaller or equal than mu naught summation EI where I is 1 to infinity. I want to show the equality. I want to show this, right? And where each EI is in A and EI the finite union of intervals in E. So this is like, or with loss of generality. So this is equivalent. So it suffice, is suffice to just assume each EI is one element in E, i.e. EI are H intervals because they are finite. So it's okay to think them just one. You can definitely argue that when there are two, but the argument is going to be very similar. Okay, so therefore, since mu naught of ui to infinity of in is equal to summation I to infinity mu naught of in. Sorry, n is equal to 1 to infinity, n is equal to 1 to infinity. This is 1 we proved before, right? We are done because in here is e. Okay, so that is proof of finding such premeasure on the algebra, which will later generate the Boreal measure on X. And then I feel like the key idea is to prove claim 1, the sigma finite additivity of the function mu naught. And then you have to show the inequality in both sides. And once you show, and it's a little bit, you have to think about A and K, B and K, or A and K plus delta B and K plus delta and K. But anyway, once you've done it, you are almost done with the with this